Hello friends, I am Dr. Sudhan Sharma from School of Computer and Information Science in Indira Gandhi National Open University, and today's session is about sequence in series, and this is continuation with our earlier session wherein we covered about arithmetic progression and geometric progression. In this session we are going to cover about arithmetic geometric progression and the harmonic progression. So objectives of today's session are in fact to understand arithmetic geometric progression and the harmonic progression. Apart from this, we are going to learn how to determine the sum of first and natural numbers, their squares and cubes. Just to begin with, arithmetic geometric progression is a special type of progression wherein both arithmetic progression and geometric progression are fused all together. That means if the nth term of a sequence is obtained by multiplying the nth term of an AP and a GP. So let's consider that there is an arithmetic progression AP wherein the terms are A plus D, A plus 2D and so on. And we are having a geometric progression wherein the terms are B, BR, BR square, BR cube and so on. So that means if we combine the arithmetic progression and the geometric progression, the first term will combine and the first term will be AB. Thereafter, the second term will be A plus D into BR. So A plus D into BR is the second term. On the same lines of action, the third term will be A plus 2D into BR square. So that means there is an arithmetic progression and there is a geometric progression. The combination of the two progressions is actually the arithmetic geometric progression. And the formula for the nth term of an arithmetic geometric progression will be the product of the nth term of the arithmetic progression and the nth term of the geometric progression. The formula for the nth term of the arithmetic progression is A plus n minus 1 into D. And on the same line of action, the nth term formula for geometric progression is B into R to the power n minus 1. So if we multiply the two terms, we will be getting the nth term for the arithmetic geometric progression. I hope you understand what is arithmetic geometric progression. Let me repeat. Let there be a arithmetic progression whose terms are A plus D, A plus 2D and so on. And there be a geometric progression whose terms are B, BR, BR square, BR cube and so on. If we multiply term by term the components of arithmetic progression and the geometric progression, the new progression which we will get is arithmetic geometric progression, whose terms, the first term will be AB, which is the product of the first term of arithmetic progression and first term of the geometric progression. Second term will be the product of second term of arithmetic progression, that is A plus D, and the second term of geometric progression, that is BR. On the same lines, A plus 2D into BR square will be the third term of the arithmetic geometric progression. And the nth term will be the product of the nth term of the arithmetic progression and the nth term of the geometric progression, and this will be the resulting formula for the nth term of the arithmetic and geometric progression. Now, the second important concept of arithmetic geometric progression, we are not going into the proofs of those, but the simple formula for the sum of the n terms of the arithmetic geometric progression is given by Sn, wherein we are getting the values AB upon 1 minus R plus BDR, where B is the first term of the geometric progression, D is the common difference of the arithmetic progression, R is the common ratio of the geometric progression. BDR into 1 minus R to the power n minus 1 upon 1 minus R square minus A plus n minus 1 into D into BR to the power n upon 1 minus R. The formula will be modified if R is equal to 1, then the sum of n terms of the arithmetic geometric progression is reduced to Bn to the Bn by 2 multiplied by 2a plus n minus 1 into D. And if number of terms tends to infinity, then the overall formula for sum of n terms, that is infinite terms in this case, will be reduced to AB upon 1 minus R plus BDR upon 1 minus R square. Now, because n tends to infinity, so this formula is simplified into this term only. Now, we will apply these formulas to solve some numericals. So let's apply the formula to find the sum of n terms of a series, which is given over here is 1, 4 by 5, 7 by 5 square, 10 by 5 cube, and so on. The simple observation over here when you are getting this type of numericals over here is that the terms which are moving in the denominator are 5, 5 square, 5 cube, and the terms which are moving in the numerator are 4, 7 and 10. So, you can see that the repeated pattern in denominator is following the geometric progression, and in the numerator it is following the arithmetic progression. So, the first term is 1. So, that means A is equal to 1, that is the first term of the arithmetic progression, and the first term of the geometric progression, both are 1. So, that's why A is equal to 1, B is equal to 1. Now, as I said, the denominator, the pattern is 1, 4, 7, 10. So, that means, and so on, that means the common difference D is equal to 3, because 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10, and so on. So, the arithmetic progression, the common difference is 3, and the common ratio R is equal to 1 by 5, because in a denominator the pattern which is followed is 5, 1 by 5 you can say, comma 1 by 5 square, comma 1 by 5 cube, and so on. So, that means the common ratio R is equal to 1 by 5. So, D is 3 and R is 1 by 5. And we already know that in arithmetic geometric progression how the terms vary. The first term is AB, the second term is A plus D into BR, the third term is A plus 2D into BR square. Now, applying the formula of the sum of n terms, which is written over here, and you will find that by applying the formula and by solving it, you find that this finally turns out to be this value. Now, one of the important observation is that in the given question, the series, the progression is non-terminating, that means it is going to infinity. So, over here if the n terms goes to infinity, then 1 by 5 to the power infinity will tends to 0. As a result of which this part will be 0. Hence, the overall answer will be 35 by 16. The overall answer will be 35 by 16. Now, on the same line of execution, if we apply, as we observed that the pattern is moving to the infinity. So, as n tends to infinity, what is the modified formula? The modified formula is S is equal to AB upon 1 minus R plus BDR upon 1 minus R square. Now, we already know that R is equal to 1 by 5, D is equal to 3, A is equal to 1 and B is also equal to 1. Substituting these values into this formula, what you will get by solving this formula, finally you will get the answer is 35 by 16. So, either way, if you apply this formula or you apply this formula where n tends to infinity, you will get the same answer. Because the observation is 1 by 5, which is small number, and to the power infinity, this tends to 0. Hence, the final result by applying this formula was 35 by 16. And when we apply the formula, then n tends to infinity, the modified formula, the same results we get is 35 by 16. I hope you understand this. Now, thereafter, let's again solve one more example. Now, directly there is an observation you can make when looking at the example, that find the sum of n terms of the series 3 plus 5 by 4 plus 7 by 4 square plus 9 by 4 cube. Now, this sequence tends to infinity. Now, in numerator, we are having the pattern 3, 5, 7, 9. And in and the other pattern is 1 by 4, 1, 1 by 4, 1 by 4 square, 1 by 4 cube. So that means arithmetic progression, the first term a is equal to 3. In geometric progression, the first term is equal to 1. The common difference d is equal to 2, 5 minus 3 is 2. So, and the common ratio is 1 by 4. So, using these values in the arithmetic progression, as n tends to infinity, arithmetic geometric progression, as n tends to infinity, the formula is AB upon 1 minus r plus BDR upon 1 minus r square. Substituting B, D, R, A in this formula and solving this value, this expression, you will get the answer 44 by 9. I hope you learned how to find the sum of n terms of a series or arithmetic geometric progression. Now, the next important progression, which is very simple and very important, is your harmonic progression. So as to formally understand the harmonic progression, a sequence A1, A2, A3 of non-zero numbers is said to be a harmonic progression if 1 by A1, 1 by A2, 1 by A3 up to 1 by An forms a arithmetic progression. So the terms of arithmetic progression in the inverse way contributes to the harmonic progression. So as to better understand this, let's solve an example. Say the example is about, say, find the 10th term of the harmonic progression 1 by 3, 1 by 7, 1 by 11, 1 by 15. So that means the denominator contributes to the arithmetic progression. So arithmetic progression is 3, 7, 11 and 15. Inverse of the arithmetic progression is your inverse of the terms of the arithmetic progression is your harmonic progression. And we know that the 10th term Tn in arithmetic progression is a plus n minus 1 into d. This is the normal formula. Now a, this is the first term is a, common difference is 4. So d is equal to 4, a is equal to 3 and number of terms, the 10th term. So n is equal to 10. So substituting these values, T10 will turn out to be 3 plus 10 minus 1 into 4 and that is nothing but 39. That turns out to be 39. So the 10th term in harmonic progression is 1 upon T10, that is 1 upon 39. So this is what is the solution over here, that the 10th term of the harmonic progression is 1 over A10 or 1 over T10, whatever you want to say the 10th term is, and the 10th term is 39 in arithmetic progression. So in the harmonic progression, it will be 1 over 39. I hope you understand this. Now, further we are supposed to move for a new concept, that is the sum of first n natural numbers, their squares and their cubes. So over here general formulas are discussed. Likewise, if we are having a sequence of numbers, say 1, 2, 3 up to n, is an arithmetic progression in fact, because the first term is 1 and the common difference is also 1. So first term is 1 and the common difference is also 1. And as a result of which the sum of first n natural number turns out to be Sn is equal to n into n plus 1 by 2. So for example, if n is equal to 5, then sum of 1, 2, 3, 4, 5 will be 5 into 5 plus 1 by 2. That is 5 into 6 by 2, that is 15. And we can directly say 5 plus 4 is 9 plus 3 is 12 plus 2 is 14 plus 1 is 15. So that means you can directly use this formula to find the sum of first n natural numbers. Now let's extend our discussion that if we are having the squares of the first n natural numbers, then what will be their sum? Their sum will turn out to be n into n plus 1 upon n into n plus 1 into 2n plus 1 upon 6. that is 1 square plus 2 square plus 3 square up to n square. If you want to find the sum, the formula will be n into n plus 1 into 2n plus 1 by 6. So, if you solve the same formula, same question again, that is what is 1 square plus 2 square plus 3 square plus 4 square plus 5 square. Then you can simply directly apply this formula for Sn, and you will get 5 into 5 plus 1 into 2 into 5 plus 1 upon 6. That is 5 into 6 into 11, that is upon 6. So, 6 will be cancelled and 11 into 5 is 55. So, the sum of the squares of first 5 natural numbers turns out to be 55. Now, what about cubes? So, the sum of first n natural cube of first n natural numbers will be given by the formula n into n plus 1 by 2 whole square. So, and what is n into n plus 1 by 2? Sum of first n natural numbers. है ना? Yes. So, the formula states that the sum of cube of first n natural number is the square of the sum of first n natural numbers. So, that means if we are having say 1 cube plus 2 cube plus 3 cube plus 4 cube and we want to find the sum, then we can directly use this formula 4 into 4 plus 1 by 2 whole square. That means 4 into 5 by 2 whole square. So, 2, so that means 10 square, that means 100. So, 100 is the sum of the cubes of first 4 natural numbers, cube of first 4 natural numbers. So, the formulas are mentioned for your reference over here. And now we are going to solve some more examples. Likewise, over here we are supposed to find the sum of 1 square plus 3 square plus 5 square to 2n minus 1 square. So, that means subsequent odd numbers, odd natural numbers. So, that means if we want rth term, say TR is the rth term, and then that will be odd. So, that should be 2r minus 1, and because it is a pattern for square of the number, so it should be TR minus 1 whole square. So, 2r minus 1 whole square, that is a square plus b square plus 2ab. We are applying the formula a plus b or a minus b whole square. A minus b whole square is equal to a square plus b square minus 2ab. Applying the same formula, a square, that is 2r square plus 1 square minus 2 into 2r into 1. So, that means 4r square plus 1 minus 4r. So, this is the rth term, this is the rth term. So, we can say that summation of r is equal to 1 to n TR will turn out to be summation of r is equal to 1 to n 4r square minus 4r plus 1. That means 4 to summation of r square minus 4 into summation of r plus summation of 1, where r varies from 1 to n, where r varies from 1 to n, where r varies from 1 to n. Now, because we are adding 1 n times, this expression turns out to be simply n. What about this expression? Over here, single power terms are there. So, sum of single 1 plus 2 plus 3 plus 4 up to n. The formula was n into n plus 1 by 2. Sum of n terms formula was this. So, this expression will turn out to be minus 4 into n plus 1 by 2, which is written over here. So, minus 4 into n plus 1 by 2. Similarly, this is the square sum of squares. So this will be 4 into n plus 1 into 2n plus 1 overall by 6. So this is the expression written over here. Because we are squaring the terms, so that's why sum will be given by this formula. For 1, 2, 3, 4, 5, 6, sum of n natural number, this formula will be used. And because we are adding 1 n times, the result will be n. As a result of which, this expression will be finally resolved into this expression, wherein 4 into 1 by 6 n into n plus 1 into 2n plus 1 minus 4 into n by 2 into n plus 1 plus n. Solving this expression, you will finally get this as a final term, 2 by 3 n into n plus 1 into 2n plus 1 minus 2n into n plus 1 plus n. Now, to further solve it, we can take 1 by 3 n as a common factor, 1 by 3 n as a common factor, and let's see what happens, how to further solve it. If we take 1 by 3 of n as a common outside, then inside we are remaining with 2 into n plus 1 into 2n plus 1 minus 6 into n plus 1 and 3 will be remaining over there. So, finally solving it, finally we solve it in opening the braces, multiplying each and every term and solving inside. The final expression turns out to be 1 by 3n into 4n square minus 1, which is this expression. You can easily get this solution by solving it as it is shown over here. Just open the braces, solve, multiply each and every term and you get the answer, which is. Now, let's solve one more numerical for your better understanding. Over here we are supposed to find the sum of the series 1 into 2 square plus 2 into 3 square plus 3 into 4 square and up to n into n plus 1 square. So, the rth term is following the expression r into r plus 1. That means r into r plus 1 square. So, that means we will be getting the expression r into r square plus 1 square plus 2r. So, that means by opening, we are opening the braces, solving it, we will be getting r cube plus 2r square plus r. So, that means the sum of rth term will be equal to tr summation will be equal to summation of r cube plus 2 times of summation of r square plus summation of r. The summation of r cube is having the expression n into n plus 1 by 2 whole square. Summation of r terms is n into n plus 1 by 2, and on the same lines summation of r square, this terms the sum is 1 by 6 n into n plus 1 into 2n plus 1 by 6. So, these respective terms are replaced over here, and we got this expression. By solving this expression as it is shown over here, following these steps one by one, you will finally find that the final solution is 1 by 12 n into n plus 1 into n plus 2 into 3n plus 5. So, just follow the steps as discussed over here and you will be able to find the sum of the series. These questions are very important and you will enjoy solving these expressions when you are going to try to solve these problems on your own using pen and paper. You are supposed to just follow the pattern, follow the steps delivered in this session and you will be able to solve the numericals. and this is all about this session. Thank you.